We have defined a linear estimator, and the criterion of mean squared error. We want to optimize that, and this optimization leads to a set of equations which we will refer to them as principle of orthogonality. So orthogonality principle is a set of equation and is obtained for linear mean square error estimation, and is also obtained for other estimators. We'll talk about it. So when we calculate the derivative of the mean square error with respect to each individual parameter, we find that mean square error is minimum when these set of equations are zero. So these set of equations lead to the fact that the data shall be orthogonal to the error. So each of xi, so you will obtain this set of equation. And this one means that the error shall be perpendicular or orthogonal to all data samples for that. In other words, if you have a vector of S you want to estimate it using a linear combination of x1 and x2, a linear combination of x1 and x2 is in the hyperplane containing x1 and x2. So a1 x1 plus a2 x2 plus etc. plus an xn is inside in P, and P is the set of all linear combinations. So is a hyperplane, is like a 2D plane or 3D plane or and so on. So if you want this error, if the error, this is S hat, if you want S minus S hat to have, which is error, if you want this error to have a length which is very minimal, so if you want to minimize mean of error to the power of 2, this vector error should be perpendicular, should be orthogonal to x1, should be orthogonal to x2, and so on. In other words, the shortest distance between S and S hat happens when the error, when S minus S hat, so this error is S minus S hat. When S minus S hat, this vector is perpendicular on P. So the error should be perpendicular to P. That means that error should be perpendicular or orthogonal to all entries of P. So error is orthogonal to all members of P. Members of P are the various linear combinations of x1 to xn. So this is called principle of orthogonality or orthogonality principle. So if you write these equations, okay, because you will have some equations, you will, for the first one, when you put I equal 1 to etc., you find a set of equations, and if you form these set of equations, if you put your unknown parameters, which are a1, a2, a1, an, and then you put a matrix here, you will have r11, etc. Then you will get r01 and so on. So you'll find a set of linear equation which is easy to solve, because this unknown becomes inverse of this matrix multiplied by this vector. So Rik is equal to this one, so each of these forces, R22 is mean of x2 times x2, and this one is mean of xn times xn. This one is mean of xn, x2, and so on. And this side, for this one, is mean of s times x2. This one is mean of s times xn. So you put this one in a vector and this coefficient in a matrix, and then you can solve it. This they define these correlation matrix. So these coefficients of AIs become a correlation matrix, and this becomes a cross correlation vector. So to solve this one, we format X into a column vector, A to a column vector, and this one you put a column vector, and then you define correlation, input correlation matrix, and then you have this equation. So A becomes equal to R inverse R naught, which is the inverse of autocorrelation of Xi's, and this is a cross correlation between Xi and S. So remember that this is R0, and this is so this is autocorrelation, cross correlation of vector X and X transpose. This is X with S. So this gives you the optimal weight vector. So once you get these coefficients, so this is like A1 optimal value, A2 optimal value, etc. Then these coefficients you multiply it by your random variables and gives you the best estimator. So from orthogonality principle, the error is also orthogonal to this one. And remember that S is equal to S hat plus error. And because these two guys are orthogonal, energy of this one is equal to energy of this one plus energy of this one. So energy of this one is the subtraction of these two energy. So I could say that this is the, once it is optimized, the energy of this one is the minimum attainable mean square error, which is equal to this value. So you can easily calculate it, and the minimum mean square error or minimum attainable squared error, which is the minimum of the Euclidean norm of the error, is equal to this one. So this is the total energy of S, and this is the energy of S hat. Remember that this is S, this is S hat, and this is error, and they are perpendicular. So this guy to the power 2 is equal to this guy to the power 2. But these two guys, the square root of these two guys is equal to this one. And this is what you see from this equation.